Hello, welcome to Chapter 2, Chapter 2 lecture video. So in this chapter, we're going to talk about kind of the conceptual ways of thinking through data, or specifically modeling the data elements. So it's really a precursor of getting your head around how we actually think at an abstract level and understanding of the world that pretty much makes up all the data any organization needs to capture, and then translate them to designs. So this is kind of the prerequisite before we go into designing of databases. So we're going to kind of visit and go through a couple of the concepts and techniques of designing database. So let's get right into it. All right, so start off with data modeling. So I want to focus on the key term here. It's the word model. So put aside the subject or the topic of database. Let's just look at the definition of model. In the world of, I guess in business, as a manager in whatever industry, as you pursue your career and work in the environment, you're gonna realize there's a whole level, different level of complexity of what we have to deal with in any organization, in any sector, in any profession, in any career. So everything that's around us is very messy, it's very complex, right? Just look at yourself as a student. Even though you haven't really journeyed into a career of any organization, just your life up to this point as a college student, you're dealing with finances, loans, schools, class, professors, transportation, living expense, what's for lunch, budget, right? Student loan, you name it. It's very complex. And every single point of that complexity that you have to interact with, or that impacts you, there's information, there's data that comes along with that complexity. So that's just kind of our our normal lives. But when you start working, you're actually, whatever role you're in, you're gonna start dealing with another layer and dimension of complexity that you never thought even pertains to you. But it does, because that's your job. So the world will become more complex, and that's why they call it stress, right? At work, there's stress work, and life, there's life stress. It's because of all this complexity that we deal with in our lives. So where does the word model comes in? Model is a way for us to look at something a little bit more abstract. If you look at and try to understand every single piece of data throughout all this complexity that hits you, and you try to understand it and make decisions at such a granular level, it's hard for you to comprehend what does that mean. In other words, like the orientation video you saw, right? What does it mean if you go out this weekend and drop $1,000 on vacation to Vegas just because you feel like it? What does it mean, right? You can look at that granular, just say $1,000 gone. I'll be happy over the weekend, and that's how I'm gonna make decisions at each transaction at a time. But then you're gonna realize, if you drop this $1,000, 2 months from now, you don't have the money to pay for gas. Would that become a problem? If you don't have, you need the money to buy the textbook for whatever classes that you need, would that be the problem? So this relationship between every single granularity of data that we look at, and if you look at that level, you cannot decipher it. The interconnectivity of everything that hits us is just so messy. So data model, or modeling specifically, is for us to understand the relationships, the pulls and the push between every element of things that happen around us at a level where our mind can actually make some sense of. And that's very important in terms of data, because data comes hard, high volume, fast in any organization in life. that you need to know what to do with and how they relate to each other. So data modeling is a way to do that. So the word model, I guess what I'm trying to say is whatever you're learning in terms of modeling technique from this class of database, the concept of having the ability to train your mind to see any complexity, regardless whether or not it's finance class, accounting class, database class, or your personal life and career and whatever that's that happens to you, you have to have a way to see the world at a model level and train yourself to do so. I'm not sure if so every one of us operates our mindsets operates at a different level. Some of us are big picture people. We default to seeing the forest from the trees. That's just the way our brain anchors ourselves. Everything that happens, we say, no, that's fine. The global economy will be fine. But then some people will be very granular. They live at the tree level. They default to that. That's their mentality. What if that tree gets chopped down? What if I lose my house? What if the interest rate increases and I can get a house? And then some people says, nah, you'll all be fine because the economy is good. So they think at the high level, the big picture level. Some people just can't help themselves and wanted to give examples, very specific things that they can get over one specific example, so they can struggle to see a bigger picture. So unfortunately, all of you as students, every one of you, I can tell you right now, you gravitate towards one of those levels. So from chapter 1, we look at the pyramid, right? The strategic at the top and then the operation at the bottom. Some people make their whole career working at the operational level and don't move up. One of the key reasons is that's how they think. They can never elevate their thinking to become what a manager is required of them to get them out of to see the forest from the trees, because everything they can ever think of is the trees. Therefore, they make the whole career not able to advance themselves. And then some people advance them fairly quickly up to the strategic level because they can actually make the connection to the bigger picture at play, right? They can see the bigger issues. So they rise up to become executives because that's what's needed for them to see and not make decisions on one transaction because they have 10 million at a time every day. So if you make your decision based on one transaction, then you're not going to be at the helm of driving this organization. So modeling is a technique and ways to really, really understand how to practice that, how to think about that. So it's my long spiel to tell you what you're about to learn in this class doesn't just apply to database. It is a concept I can tell you personally. I use modeling techniques across everything I do as an executive, and I don't do database anymore. It's I just teach this now because my career early on in my career that's what I do, but the last 15 years I haven't touched and created a database schema because I move up. So as you learn this, make sure you kind of see what you're learning as a true skill set that you can acquire outside of just knowing how to design database. All right, so 2 more things I want to add before we move on. So just definition, why I kind of focus on the word the model. So definition of the term model is a model is like a model of a system or a process. That's a theoretical description that can help you understand how the system actually is without get your head around the complexity. So it simplifies complexity. Einstein has a couple quotes I really, really like. So Einstein says, if I had an hour to solve a problem, I would spend 55 minutes thinking about the problems and only 5 minutes to think about the solution. So I think that is where, to me, that phrase actually describes a little bit of to elevate and see things through to find the solution to whatever. You actually, before you can rise up to the modeling, you actually have to go down and understand all the moving parts with the goal that you're going to spend a lot of time learning this detailed stuff but don't lose sight that you are learning all this and having to get your hands in there just to understand how to elevate it higher. So to me, that's a good quote. And then he also had another quote that he says, if you can't explain anything, or if you can't explain it simply, that means you don't understand it well enough. All right, so those two quotes kind of anchors as you go through this. You're gonna understand we're gonna get our hands into the nitty gritty of what data design and data modeling and the techniques, looking at the tables, the data, the attribute. But then always remember, you have to learn all that just to elevate higher to understand why the modeling of abstraction is so important. All right, let's move on. I'll kind of beat that horse. Importance of data modeling cannot be overstated. So I kind of cover a lot of that. It does facilitate communications, right? At the end of the day, if you show me a picture, it's worth 1,000 words. It's hard to use vocabularies to achieve meeting of the minds between people, to achieve agreement between people, because they're just words saying, communicating in words to describe something very, very complex you'll lose your audience almost immediately. So sometimes, an abstract description of what is happening is easier to convey and it's more efficient. Give various views of the database, of course. Once you have a conceptual representation, then you can look at it from different perspective, which we'll have some examples down the road. He organizes the data that's meaningful to users, and you will see what that means later as well. So abstraction, so on and so forth. All right, let's move forward. All right, some of the definitions. As you read through the chapter kind of describes it. So make sure you go through the textbook. But right now, for lecture purposes, I might hit this a little bit more faster than you can kind of catch up or stay stay with the description. But it'll come to you as we continue to progress. But right now, it's just more definitions. Entity is a person, is a place, or the slides will say it's just nouns. Every time we look at what does the business interact with, what do we do as a business, who interact with us, where are all the points of informational data gets generated as we conduct our business with whoever we conduct it with. So as you think through that answer, you're going to have a lot of nouns that come into play, right? We got customers, we have vendors, we have locations, we have, Eastville sites, we have Riverside sites, we sell coffee, which are things, right? So as you kind of talk through what you do as a business, you're actually popping off and describing a lot of entities that you interact with. So the term entity is important. We try to understand what are all the entities that actually involves in our business. And then each of those entities obviously has attributes, right? Characteristics that we need to describe what those entities are. So explain to me what does customer, who are the customers? Who are they, right? Who are they? Where are they? So as you describe those one entity at a time, those becomes characteristics of that entity that you need to understand. So we call those attributes. And then between those entities, there's relationships, right? So we have customers, we have sales agents. What's a relationship between the entity sales agent, which is a person or people, and the customer, which is another group of people? What are their relationships? What do they do, right? How do they interact? So those are relationships. There's actually 3 types of relationships that can never exist between every relations inside the context of database design. One to many, many to many, and one to one. So what does that mean? That means, so between my sales agent and my customers, what are the relationships? There can only be one of these 3. So if I were to say it's one to one, that means every sales agent will only have one customer. Every customer should only have that one sales agent. Therefore, the relationship between these 2 entities is one to one. Or I can say, you know what, each of my agents can handle multiple customers that I'm going to assign to them. So I'm describing the entity relationship. So each agent will have multiple customers that they need to handle, but each customer will only have one agent. right? So that's a one-to-many relationship, or many-to-many, right? Each agent can have many customers, and each customers can deal with multiple agents at a time. So that's a many-to-many. So in a nutshell, we simplify, right? So we just talked about how my business conducts itself. I have agents, I have customers, and then their entities. So agent, customer are entities. Their attributes, right? Who, describe agent, what their qualifications, what their phone number, what their location, blah, blah, blah. That describes the agent. And I can do the same for customer. And then I define the relationship between them. Now, the important definition here is one of the important ones is constraints. Constraints are important because they help to ensure data integrity. So definitely that's an important concept. Make sure you understand the definition of constraint. Constraint is put on top of any of that element. Constraint is also what makes the data jive as we design database, meaning we won't have any discrepancies and or anomalies that we learned from chapter 1. Constraints puts certain rules around it that will make sure we have data integrity or minimizing any data anomalies as we capture them and store them and utilize them and transform them into information and knowledge and wisdom and so on and so forth. All right, so one example I can give you, some of the constraints that we put around data is, let's just say, can you have 2 social security numbers from IRS? The answer is no, that's a constraint. Everybody throughout the life of their existence here in the United States, you shall only be assigned 1 social security number that you will use for the rest of your life. That's a constraint, right? You can't just create another one. Can you have 2 student IDs at UCR? The answer is no. That's a constraint, restriction placed on data. That particular data relating to you as a student should only exist one time and forever. So that ensures the data integrity, because throughout your existence, we're gonna leverage that one assigned value to you to represent anything and everything about you. So that's an example of what a constraint would be, all right? Very important concept, and you'll definitely see more and more of that coming up in later chapters. All right, so business rules, which is part of the constraint, brief, precise, and unambiguous description of policy, procedure, or principle. All right, so business rule is very stringent, is how business establish themselves, is how business conduct themselves, and they create enforceable actions within the organization environment, establish entities, relationships, and constraints. So how does that come into play? If you think about it, business rule is very unique to every organization. In other words, if you go to Nordstrom and you work as a cashier, they're going to train you anything and everything about the rules, their business rules about how you should be treating the customer, what's acceptable, what's not acceptable, and what kind of transaction, how to handle the transactions, and then how to handle the kind of transactions, how to handle the, for example, if a customer comes and return this product, your business rule, your policy is you're going to let them return it as long as it's within 20 days or 30 days of purchase. But if you go to Macy's, their principle, or their procedures or policies maybe as long as they purchase within the last 14 days instead of 30 days. So you can see every organization has different business rules pertaining to the entities, the transactions, the relationship, or what they do with throughout their transactions, throughout their business or conducting their business. So business rules are unique to organizations, which places a different constraints on the data as we capture them, allow the database to do certain things to the data because of rules. So it is a very important source for us to get our head around and truly understand them as we come in and build a database design to capture data for the organization. So example, what else? let's just say, I don't know, for some classes, as a student, C minus is still a pass, but anything below C minus, you have to retake the course. Um, or some college may say C is a pass, and C minus you have to retake the course, right? Those are different business rules for different universities, so you can kind of get a feel for there's a uniqueness of business rules, and this is also just kind of a one more thing on this topic. Business rules is actually what makes up the competitiveness. If you really think about it, whether or not you buy coffee at Coffee Beans, or you go to Starbucks, or you go to McDonald's selling coffee, the business of what they do and how they do it are very similar, right? They have a point of system to capture it. So everything that they can capture about what you had bought over at Starbucks and all the data that goes into that database is probably going to be the same as when you go to Coffee Beans and they captured almost identical data. So if you really look at it, all the businesses capture pretty much the same stuff, which is as much of data they can capture from every single customer and transaction. So everybody is pretty much at par there. But why does one company still outperform the other when they have the same data that translate to maybe same information, maybe, and they make decisions against them? Well, that's the thing. The business rules are different. Business rule is part of a strategy. If somebody allows 30 days, I'm going to allow 60 days return policy to offer more customer friendly policy compared to my competitor. But what does that mean? That means my database had to accommodate to allow that rule. Otherwise, my database is going to say, nope, this one is past 30 days. I'm not going to let you make changes, because policy says 30 days you cannot void or change or refund a transaction. Well, those are rules that's built into the database. That database won't allow you to do certain things. But if you need to change the strategy, then we change the business rule in the database, and then database will then allow a different criteria to enforce its data integrity against the rules. So that's kind of one example to say why business rules are important, and they're unique, and they play a big part into your understanding of how to design your database for very specific or every individual client that may make or break the ability to compete. So anyway, so that's business rules. So where do you get them? Well, company managers, they should know their rules, right? They're the one that's running the operation. They should know their policies. They should know their business constraints and whatnot. And they're a source for you to interview as you try to design a database for a company. You want to meet and hear them out. Or the executive, the one that makes those rules at the higher level, the policymakers, the department managers, documentation, right? Usually, if if you try to interview and work with a big organization that want to design a complex database, they should have certain levels of documentation that capture all that complexity into a written format that you need to read through them all and understand them all. That will come into play, helping you understand the relationships and how you want to design the database accordingly. And then you meet with people and then just get it from them. So we call that a little bit more of a pulling out, or social engineering, to pull it out of people's head, and tribal knowledge, right? Sometimes, Tom been here 20 years, he knows everything and anything about how to conduct that business. But guess what? It's all in his head. And you have to now go pull it out of his head, assuming he's willing and articulate enough to explain it to you that you can understand it. Right. So that's a problem. Organizations sometimes don't have a documentation. Therefore, you have to resort down to meeting with people and try to ask the right question to pull the stuff that you need out of their head. And then discovering business rule. Let's see what else. So again, formal definition, business rules, right? From a database point of view, is a collection of data becomes meaningful only when it reflects properly defined business rules. All right, very important. Your data had to reflect the business rules when you capture them, when you design them. Otherwise, data is pretty much stagnant or devalued its capability of informing you certain information. So business rules are integral part of this. Make sure you get your head around that as you read through the chapters. Let's see, facilitate communication tools between user designers. What else do I need to cover here? So once you document them, right, you can validate them, you can communicate them. Anytime you have a documentation, it's always a very efficient and productive communication tool. When you don't have anything documented, that becomes harder to convey and communicate to others. So that's why, example is, that's why we as a policy from UCR, we always have to have a syllabus with our class policy that I established for my own class. I have to have it written. So school usually don't allow us to verbalize our policies at the first beginning of the class without something written, because something written is easier to understand. You can comprehend it. Words are very precise, and there's less of ambiguity when you have a written document. So it's kind of the same concept. All right, so let's move on. Translating business rules to data model. Business rules set the stage for properly identifying entities and whatnot. So as you hear and interview and talk and read through whatever the artifacts that you can get your hands on about how they do their business and the rules and policies and so on and so forth, you're going to see nouns in those writings. When customer approaches the counter, you blah, blah, blah. Just reading that one sentence, I already know customer is a noun, and therefore customer is probably an entity that we deal with as a class, as a grouping of what we do. And then any verbs translates to relationship. So the customer can place orders with any one of our store. So that phrase, as I read through that, or as somebody tells me that from the business, even though they say it as a way of it's a business rule that every customer can go into every storefront and execute a return. So customer is a noun, that's an entity. They can do a return, that's a verb, which means it's a relationship. A relationship to what? To orders, right? Any customer can execute a refund on their order. So order is another noun. So between customer, order, and whatever else, right? I see the relationship. It's a refund process, which is a verb. So that is how we acquire the basic understanding of what's happening to any business, that started to formulate a data model in our head, conceptual model in our head of what is going on. And then we diagram that. So that's kind of the initial stage of process of try to design a database for an organization. Relationships are bi-directional, right? So customer can request a refund on an order, or they can place an order. So those are our relationships. So how many instances of B related to A? I have a diagram that will show this. So keep this one in mind. And then once you see the visual, you'll be easier to understand the relationship aspect of it, which is a few slides more down that will come back to that one. All right. Naming convention, some of the standard ways of making sure we design our database very clearly, very efficiently, effectively is, we have to standardize the way we name things. So entity name requirements be descriptive of the object or the group, right? Customer is customer. If you have multiple different types of customer, like you have business customer, you have retail customer, you want to be very precise. Those may be two separate, distinct entities. So you don't want to just call it customer one, customer two. You want to say business customer and then retail customer. So there's certain naming convention and terminologies that as a database designer, you want to make sure you're very consistent about, so that everybody that can pick up your design can actually understand that standard and really see the consistency as they read through your design. Same thing for attribute names. You want to be very clear about your attribute naming convention. So at the end of the day, right, it's just good business practice. Otherwise, people have to decipher your inconsistency in your design, and then that's just very, very inefficient. So the example I can give you, right, if imagine if I don't know if you know, to become an architect here in California, you have to pass, I think, 7 exams at the state level to be given a license to practice as an architect. And part of that test is very hard. But one of the things they're testing you on is just uh, how well do you understand every single thing, every single standard about drawing a blueprint, and what you need to consider, and how you name everything on the blueprint. So that's a standard way of drawing a blueprint here in California. So you get tested so much that every single architect that's licensed here in California should be able to draw a blueprint that any subcontractors that actually builds the house or the buildings looking at any blueprint can immediately understand every single blueprint, even though it was designed or drawn by different architects. So the standard of naming and the standard of diagramming, of drawing, of using the symbols, of using certain calculations of any design is the key for universal understanding of what you are trying to design. Because usually the designer is not going to be the builder. And each builder may build against designs from hundreds of different designers. Each designer's work may be disseminated to all kinds of different builders. So think about it. If every architect like to draw their own things using their own personal standard, and then without a uniform way of doing it, then when they send out the blueprint to have whoever that's willing to build it for them, they had to spend a lot of time educating their personal standard of how they drew the blueprint. Which makes building any building very, very, very inefficient and costly. Not to mention, it's going to make a lot of mistakes building it because the design is so unique to that that designer, that nobody truly understands it. There is no meeting of the mind against the design. It's too hard to do that. So same thing with database, naming convention, standardization of how we approach thinking, designing database, and then eventually building them. The protocol and standards are very important here. Hierarchical, I'm not going to go through this as database that's kind of a little bit outdated. Still exists for sure, but again, I'm going to home in and focus more on relational concepts here. So I'm going to skip over this, let you kind of just read through the textbook on that. All right, so let's go through. So after the hierarchy, there's a relational model. So relational model is a little bit different than entity relational model. So there's two types of relational models. Relational model is a little bit early on where we realize, hey, we can keep data in a certain way that's a lot more efficient for us to organize the data element. So we designed databases using relational model early on, which the key thing is every single data point, every single transaction, every single engagement of us conducting the business generate data. We figure out that if we slot those data into something that looks like a table, right, like an Excel sheet table, that we can give certain names at the column level, and then we just keep on adding data that in that data table, we can organize it pretty effectively, pretty efficiently. And then if we have another set of data that doesn't really relate to this set of data, we create another table. And then we insert all those data elements in that table that's responsible to capture all that type of information or data points. And then we just keep on creating tables, and then we make sure that we can reference the tables as they interact with each other, as they have relationship with each other. So the relational model actually looks at the data very granularly early on, because we realize, hey, we got a lot of data we can capture through this whole technology database stuff. Let's just start organizing. So think about that early on as, hey, all of a sudden we bought, we're able to buy tons of shelving space that give us a lot of ways to put our folders, our paper and whatnot. And we're so happy that I want to dub this shelf as customer, folders. I want that shelf to be, our supplier information, and I want that shelf to be our order information. And then as information comes in, we put them in a folder and we start putting them on that shelf that we categorize. So each shelf is like a table in an Excel sheet. And then we just keep on adding things that pertain to that into that table. So early on in the day, that's pretty effective, that's pretty efficient, and it allows us to accumulate a lot of data into the computer world, into the database. But then, business is a lot more complex than that. And then as you build up your tables, you build up your folders on those shelves, you realize, wait a minute, when I look at this order, all this order information, who's the customer? Then you have to look at all the orders and then find out, wait, if I want to know who the customer is that placed all these orders, the only thing I have is a customer name on each of the order. Now I got to go to the customer shelves and then go dig through all that paper to find out who has that name. So even though we have a simple way of linking, each order has a name, and then the name will tell you who the customer is. Then you go over to the customer table or the customer shelf and find out that customer, all the information about that customer. That's enough for us to describe the relationship, but there's a lot more missing with the way we shelve all this data in the relational based on table. So in a nutshell, early on in the days, it was good. We create a way to capture all this information, all this data. We organized it the best we can, and then we know how they relate to each other at a very granular level. But then as data pile up, it becomes inefficient. There has to be a better way to get to this information, because early on in the relational model, we think from the ground up. We look at granularity first and then design upwards, and we realize, we can't see the forest from the tree anymore. We're in the tree level. We got all kinds of trees, group them, and so on and so forth. But I'm having a hard time seeing the forest. And then again, if I can't see the forest, I can't decide how much land I want to use. What area should I plant what kind of tree, because I'm chopping down too much of this type of tree. I can strategize. So there's certain business element, business concept that was lacking with the relational model, which then, before I jump into the entity level, so let's continue. So that's where we have some limitations. But relational model actually give us the precursor, right? The foundation to evolve the way we design database to a much, much more efficient or more modern. So we'll get to that, but let's finish the relational model here. Let's see. So we call it relational database management system. So that gave us the architecture of how to design databases that utilizes relationship and tables concept. So it gives us the foundation to do that. So you allow the database can now perform basic functions, makes relational data model easier to understand and implement. And then at that time, it was very, very useful, very powerful. It really, really solves a lot of business needs pertaining to data information. And then it does high complexity, so on and so forth. All right. So here's what it looks like. So coming back early on when I told you, we're going to look at a graphical example. Here it is. So in a nutshell, what this is you have two tables. One is called the agent. So think about this as an Excel sheet. You have an Excel sheet that has agent as the tab, and then you have another sheet called customer as a tab. So in a relational model, each column is the attribute that describes what agent is. So imagine up on row 1, column A, you're going to have agent code. Column B, you're going to have agent last name. Column C, you're going to have agent's first name, and so on and so forth. So those are the attribute that I want to capture in the agent table, which is a spreadsheet, right? So, and then anytime you have an agent that you hired, you put in all that information in one row, and then now you have one row of data pertaining to one agent that works for you. And if you have 20 agents, you will have 20 rows of data populating that table. Same thing at the customer side. So you on the customer tab, you will have the same thing, a customer table that has the attributes of code, last name, first name, so on and so forth. And then if you pay attention to the connections between the two tables relationship, right? Remember, I give you the example, each agent, one, may have multiple customers. So for us to know if you are a customer, let's say if I am a customer, Ken Wayne, my initial area code, blah, 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 one of the attribute in my record within the customer's table is agent code. So who is my agent? Well, my agent is 001. So who is 001? Then you switch over to the agent table and you look up agent 001, who's John Doe, whoever, that's my agent. So that's how we link. We actually insert a data attribute that links between these two tables. So that's at the early on, the relational model concept, that was what's created, which creates the foundation for entity relational model that all built on top of this architecture, this framework, or this foundation. So more on this, so this is pretty much the world that we're going to live in for the rest of the course, is we're going to look at a lot of this type of relationships and entities and tables and so on and so forth. All right. So let's continue. All right. So now in implementation, so in the world of database, we actually don't use Excel sheets to implement this. We have to implement them using a database software. So what does a database software need? Database software allow us, it needs us to write SQL language to implement that design, that basic concept here. So, so it's not just opening it up and type it in on column A, column B. So you don't actually have an Excel sheet looking like a tool set. You actually have to write code to tell the database to create those for you. So a database, a SQL relational database application allows you to, it has an interface for you to interact with the data, to create the data, create the tables, and then create the relationships and so on and so forth. So those database applications or tools, they actually have a SQL engine, structured query language engine, that allows the application to understand what you want to do. So you literally are, it's not really programming, but I'm just going to use the term programming. You're programming how to create and implement a database, and then the engine will actually execute and follow your instructions that you have written into SQL engine. So more on that in chapters 7 and 8. So I'll teach you some of the basics of all that stuff. All right, let's move on. Let's see here. So now we're going to add the word entity to the relationship model. So entity relationship model is pretty much everything we just talked about in terms of relational model. The key focus here is how do we derive at all those entities? All those tables, and how do we better understand and capture and describe those relationships between them? Because remember, right? At the highest level, we can look at the trees and then we can make sense of how we want to organize the trees. So entity relationship modeling allow us to now look at the forest, and then we can decide what the trees we want. So this is a little bit, I would just use the concept of top-down approach, because business requires us to see the horizon, right? To strategize into the future, to capitalize where we want to go. And then the database actually had to facilitate that. So you can't just decide on a strategy and then start doing it and then run into problems with your database. And then you figure out and firefight, how do I make my database support my strategy that we want to pursue? So think of this way as, if I want to describe from the 30,000 foot level how I want to plant my trees, what's my vision of this whole forest. And then we design a database that can actually facilitate you getting there or you being there in the future without breaking the data architecture. So that's my way kind of try to get you conceptually understand entity relationship model as that layer of higher view as a starting point in your design, which is much more effective. So entity relationship model uses the term connectivity kind of in place to relationship types. So some terminology changes, but they're similar. They kind of try to articulate the same thing. Remember, right? This is kind of traversing through time. So as time evolves from relational model to entity relational model to object-oriented modeling, you're gonna see some terminology change, but they actually conceptually are trying to do the same thing. So don't get too confused and hung up on this wording changes as you read through the chapters. So entity relationship model is a diagramming technique to present the relationship at the entity level, at a modeling level, right? So we model the entity first and then we go downwards. So it's a graphical representation. We call it the ERD, entity relationship diagram. Uses graphical presentation to model a database component. So entity instant, so this is probably, you're gonna do this, you're gonna do a ERD diagram for this class as your group project. So there's another a lecture that will kind of walk you through this. I'll give you a full example of how to do them. So you'll be a project video. And then what you will do is you will take that skill and then go apply to another database that I want you to actually draw the entity relationship diagram against. So more on that when I get that video up, but part of your assignment is to create an ERD diagram. So what does that actually look like? So here's 3 different standards of drawing an entity relationship model diagram. Again, entity relational model uses connectivity. So this is what connectivity means, or relationships. So early on in the relational model, we call this relationships, and now the term switched to connectivity. So 3 different techniques or standard way of drawing an entity relationship diagram. So let's look at one of them. Let's look at an easy one here, employee. So we have employees that manages the store, so you can get that. So somebody just told you that, the narratives of what they do. So based on that sentence, I know you have employees as an entity and you have stores as an entity. So I created 2 entities represented by a box, and I labeled it employee entity and store entity. So what are the relationship between them? Well, you said employee manages a store. And then each store is managed by an employee. So the keyword is right? An employee can manage a store, which is 1, right? Each employee can only manage 1 store, assuming that's what I heard. Each store can only manage by 1 employee. So each store has 1 manager, which is an employee, and each employee that's a manager can only manage 1 store. So therefore you have 1-to-1 relationship. Each employee manages 1 store. Each store is managed by 1 employee. There you go. I established the connectivity or the relationship between the 2 entities. So if you were to do Chen's notation standard, this is what it's going to look like. A 1-to-1 relationship between employee and store, and the relationship is managed. If you do crossfoot notation, you will use this sample here. Employee manages store, and store is managed by employee. The only thing different here is the cardinality, which I will get to in future slides. For right now, this is just a visual, so you can kind of see what it looks like. And then if you were to use the UML class diagramming notation or standard, this is how they require you to draw the same relationship. So there's 3 probably predominant ways of drawing the ERD. So you'll choose one and then you'll implement it. So for this class, I'm asking you to do crossfit notation, which I'll get into what you need to do in the example for the group project. So crossfit is what we will be using for the assignment. All right. So that's just an example of what ERD actually will look like. The only thing I will add to this is each businesses don't just have 2 entities. So by the time you're done with it, you're gonna have a lot of entities with tons of lines touching every single one of the entities. Not every single one, but most of them. So I'll give you an example. In my daytime job, our Riverside County property tax system, we have a database for the property taxation system with, I think, about over 1,000, almost 1,500 entities. And most of them has multiple lines touching each other. So that tells you, as an architect of database, if you're the only person that's going to design a database for Riverside County's property taxation system, you're talking about drawing 1,000 to 1,500 entities on a diagram, and then other people is going to understand what you're trying to do and actually build it out that way. So that'll give you a little bit to see how complex this can get based on the size and scale of the database you try to build. But this is the simplest form that has all the needed component, and then you use the same diagram here that you see. You just have a huge, large volume that you had to go through, and so on and so forth. All right. Then there's an object-oriented model technique. This one is a little bit more abstract than the entity relational model, but this one is also very effective. The key difference between the object-oriented model and the relationship model, entity relation model, is it gives a lot more efficiency to data access and retrieval. The concept operates kind of the same. You look at it from the top down, looking at the entities. Instead of entities, object-oriented model looks at it as kind of like a class. So again, terminology changes, but then the concept is kind of the same. So keep that in mind. It's just the world of object-oriented data model, they like to have their own standards, their own naming conventions, and their own ways of describing a lot of stuff. So you're gonna see something that's a little bit more foreign here under the OO, the object-oriented concept. I will put up a quick video it's a couple-minute video that somebody else tried to give you a little bit of the differences between the two. Hopefully that will help you kind of get your head around it a little bit. It's a little bit harder to get your head around object-oriented data model. But those are, I'm not going to focus on this other than you just have to get your head around from chapter 2. I'm not going to deep dive into actually asking you to do anything with OO as a project. We're going to focus on ERD, entity relationship model, because that is, again, 80-90% of things that you may see out in the real world. But object-oriented are still important for you to get your head, at least understand the concept reading this, is because they do exist out there. They do have a design artifacts that may be using OO concepts. So at least understanding the concept behind it will be helpful. All right, what does that look like? So instead of entities, they use class. And then instead of true relationship, they use hierarchy, which resembles upside down trees, which I'll show you a diagram in the subsequent slide. And then they use inheritance concept as opposed to attribute concept to describing entities. So instead of each entity has its own descriptive of attribute describing the entity that's housed, all those data element that describes or is captured for the entity is housed together. The object-oriented uses an inheritance model to separate those. Which gives more efficiency. So OO was pretty popular is because it allows you to retrieve. It evolves and solves some of the challenges that ERD creates or entity relational model creates. Entity relational model is good, but they're expensive, meaning you need to buy a lot of horsepower to get data, to capture data, to retrieve data, because how ERD or entity relational model operates. Object-oriented model want to solve the inefficiency of computer power to retrieve and access data. So he came up with a new paradigm of thinking through this and then architecturing it to allow that efficiency. So that's the kind of the underlying key difference. So they're different, and then that offers different capabilities based on how they architect and implement this. So that's where unified modeling language comes in. So remember, if you do OO based, you have to use this one. If you want to do object-oriented database architecture, then you will want to diagram your design using UML class diagram notation. But if you're doing relational model, you will use this other two. All right, so this is what it looks like conceptually, object relationship diagram. So early on, we'd say, right, everything is kept track in the table, and then we have, which is an entity, and then we have attributes describing it. Object-oriented is a little bit different. So just quick example, right? We start from the top, the global view of the things. So when somebody says we have employees, and the employees all have first name, last name, and so on and so forth. And then we give them different titles because they work for us under different job classification. So in the object-oriented world, we look at employees as the global, right? Everybody that works for it is an employee. But then we started to look at this entity and say, wait a minute, who makes up the employees? Well, we have managers that are employees. We have staff that are employees. We have teachers that are employees. So we started to create this other classes or child as a derivative of employee. Now, all the attributes that describes what an employee is stays up here. So when I try to describe what a manager is, anything that is already described inside the employee, I don't have to worry about when I try to describe what a manager is. I can inherit everything that's already designed for employee class. I can inherit it into the manager. So the manager don't have any redundancy, any other things that I need to worry about in terms of attribute, other than things that are very specific to manager. For example, office space. So I may just, one of my attribute to manager class would just be the office location, because only managers have offices. Employees don't have offices. So employee don't care and don't track anything about offices. Employee just tracks social security number, first name, last name, blah, 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 address, and all that stuff. But when I try to describe a manager, I inherit everything from employee, which every manager has the same information. But then I just need to worry about for managers where their offices are at. So you can see through inheritance, we don't have to rethink, rehash, reanalyze, and recapture anything that's already described through this hierarchy of thinking that they call, parent, child, or inheriting from the parent, all the attribute information needed, and so on and so forth from the global level. And then you just continue to kind of dig down into anything else you can inherit without having to rethink, and then you describe your business through this hierarchy of objects, and then how they relate to each other or derive from each other. So it's a very different ways of thinking, but it does offer very unique. When you implement this database in the object-oriented method, it does allow you to go straight and pinpoint to what you're looking for without looking at a large table somewhere in that table with 1 million rows of record is what you want. So in a relational database model, when you try to go retrieve something, there's certain overhead or cost of your computing to try to find it in that whole stack of a million record just to pull it back to you. Object-oriented allows a technique that can go straight to what you're asking for without that much of an overhead. So, but to achieve that, you have to design your database through this OO approach, and so on and so forth. So that's the extent of I want to describe this. As you read through the chapter, that's all you need to kind of get your head, kind of get a feel for it. But we probably won't come back and see OO in any more detail than this. All right. So I'm gonna skip this. Yeah, you can look at that, the difference. All right. Object relation, I'm gonna skip this one as well. All right, let's move on to a different subject within the chapter, big data. So remember, you learn about, we have all this database throughout different evolutions of how we track, store, and evolving our techniques of creating more efficient ways of capturing, reporting, retrieving data. Throughout this decades and decades of database, we have acquired a lot of data. So now there's, the discussion of a big data. We have large amount of data coming from every other direction. What does that mean? So as you see, we live in the world of technology. So what that means is any organization are dealing with a certain level of big data, assuming they're at the scale, being an enterprise. That means every day they have high amount of volumes of data coming into our organization database. The volume are big, the velocity of how much is coming in, and the variety of data that's coming in are all big, large in scale. So that's known as the 3 V's under big data. We'll visit a lot more in detail in chapter 14. But for now, the definition of big data or characteristic of big data is the 3V, the volume, velocity, and variety of data. So a couple examples, right? Volume. Starbucks has volume. Imagine how many transactions they do globally every single day. That's the volume of transactions their databases are trying to capture every single store, every single second as they open up for business. Velocity, how fast they're coming in. So because of volume, they're instantaneous, right? When customer comes in, you punch in what you order, that data has to handle the processing, the payment, the credit card instantaneously. So the time element, velocity, needs to be quick. It's coming in fast and furious with high volume. So velocity is happening for companies like Starbucks. What about Google? Google also has velocity problem, right? People are executing searches and then they demand millisecond results every time they search something. So that's velocity problem. And then variety, right? What kind of information are you uploading into Facebook? You can upload image, you can write a text, you can cut and paste, you can put a link, you can put a video, you can put anything, right? JPEG, GIF, file format, MP3, MP4. So you have a variety of different file types that's coming into your database that you need to track and store and retrieve, and then know how to organize them in your database. So those are the variety of data, style, and format coming in. So between the 3 or combination of all 3 is what large enterprises are currently dealing with. Not to mention, if you're Apple, right, everything you're doing right now on your phone, some data is being sent back with everybody holding an iPhone right now back to the Apple database, all right? So not only humans are creating data that's volume, velocity, and variety, things, just devices are cranking out data that's not really generated by any human beings. So those data are piling up as well. So big data is pretty much what we're dealing with. But along with that, big data provides a lot of opportunities and opportunities to data mine and discover information and knowledge and wisdom out of all the stuff that we have acquired All right, so more on that in chapter 14. I will probably share a little bit of what that actually looks like, some of the systems. Some concept of challenges. So expensive, right? With such high volume of data, we had to put them somewhere on the hard drive. So we're talking about terabytes, petabytes, and zettabytes, whatever that is. So it's a problem. It's expensive, and so on and so forth. And then it's a lot of overhead. So relational database, big data is what kind of breaks the relational database concepts a little bit, because remember I mentioned earlier, relational database concepts is very heavy on the hardware, the overhead. So having big data as a dimension of your relational database becomes more problematic. Because of that, a new concept of databases started to emerge, which is called the Hadoop or NoSQL database or MapReduce and so on and so forth. So we will visit this in chapter 14 as well. However, for this chapter, you have to understand at least, kind of what are this conceptually, what are this technology trying to do? Especially NoSQL, I think is definitely at the forefront of all that. Hadoop is also another one. So conceptually, we'll walk through what they look like, but we're not gonna go into the technicality of it. So make sure you understand NoSQL. It's not based on relational model. That's why it's called, say, NoSQL, no structured query language database. It's not gonna use that concept at all. So it's completely different ways of thinking about how to store and track database. So make sure you understand some of this, the concept benefits and why, why they're different. And then we'll talk a lot about, in chapter 14, we'll talk about, why it's meaningful, why it's useful to start journeying down that path for some organization to use non-relational database concepts. Let's see. I'm gonna skip this one. Hierarchical. I'm not gonna talk about that one. I'm not gonna talk about network. So just a recap of relational model. Advantages, disadvantages. I'm not gonna go through it. I think I hit a lot of them already. So make sure you understand this. I'll let you read through that. And then, right, from relational model, then we have the entity relational model concept, the advantages and disadvantages. So make sure you you read through this and understand this as well. And then the object-oriented as a recap. Only thing I didn't talk about is the learning curve, right? Getting your head around object-oriented approach is a little bit of, I call it the mental gymnastic. Some people is not able to kind of make that abstraction view because they're very specific. It goes back to my early discussion. Each one of you comprehends information in a certain unique way. And sometimes object-oriented may be harder to comprehend for certain people versus the other type of people. That's how their brains are wired. But again, some advantage and disadvantage here that you can get your head around really quick. NoSQL, right? Make sure you understand this as well. I'll say, even though it's completely different, in a nutshell, what is NoSQL is trying to do is try to shift a little bit away from having so much burden on a database management system to be the governance, to be the facilitator of data information inside a database. So those database application owns a lot of control, which adds a lot of overhead. And then the overhead is what hinders a lot of organizations to pursue big data. So NoSQL is trying to remove all that overhead from the data management responsibility to the programming side, kind of bypass that middle tier of database and then shift that burden to the programming language. That's why he says complex programming is required. So, and again, go through some of this from the textbook, and then you'll give you some more information on that. So this is a diagram. Let me skip that one. I have a table view that's a little bit easier. Where's that? Oh, maybe I don't. All right, so let me come back here. So in a nutshell, this is try to give you a view of going from the high abstraction all the way to more detailed, more logical, more physical, or granular view. So from the user, they look at the world very simple. They don't understand the data element. They just say, I go into the store, I buy what I want, and I walk out. So in their view, it's very abstract, right? What they do. So you have to take that external abstraction and start modeling them into a conceptual model that makes sense, right? Simplify it, group it, model it. So you can describe certain level of complexity from the abstract narrative into something that's visual. And then, but then having that visual may make sense from a conceptual model, but then you have to start translating that diagram into an internal model, which your technical people, your business people, your programming people can understand. Because again, remember, the programmers are not really business people that can understand business stuff. So the language between business person and customer talking to a technical guy, you need some translation. So think of this layer as that translating point where you take conceptual side of it and try to translate to the technical side of it. And then later on, you need to really outline how to implement this physical model to programmers that can actually do something with it in their world of programming and SQL language writing. So this is kind of what it's trying to depict all the way from the abstract to the physical, the actual programming and the code and the hard drives and on the computers and so on and so forth. So external, that's end user view. So very straightforward. You use diagramming to try to capture that and articulate and communicate that abstraction. And then you translate them to internal model. That's where the ERD comes in, entity relationship model. So taking all that external narratives, and then you're gonna diagram this. So this is at the first level of distilling your abstraction. So for example, this one is student and class relationship, right? So student, as you are students, so that's your entity. You're taking classes. So a course is like Business 173, which is the one you are taking. So in our database, we have what Business 173 is all about. But when we take each one of those courses, we offer multiple class or multiple sessions throughout the quarter. So I may be teaching 2 different classes of Business 173. So the course only has one record that describes what 173 is, but we actually have to create multiple classes. So one to many, right? And then you have a student that can be enrolled into the classes, right? So your enrollment, so each student can have multiple enrollment. You can enroll to many classes. And then each enrollment is to one specific class that you enroll into. So that's how you read that's how you read this. So class, and then we have, for each class, we had to schedule a room where we're gonna actually hold the course. So course 173 is offered 2 classes. First class, session A, is in room, right, Olmsted, whatever. Second class is offered at Anderson Hall. So we need to have a relationship between the rooms that's available to hold the class. And then one class may be taught by Professor Wayne, the other class may be taught by whoever. So even though both are Business 173, I may not be teaching both of them. We assign different class. So you kind of get the concept. Make sure you get your head around how to read this diagram, and then we'll talk more in chapter 3 as well. But this is kind of the starting point to get your head around what this looks like. So between students and class, each student can take multiple class, right? Each class can have multiple students. So if I just look at student and class, those are many-to-many relationships. All right, so let's see, conceptual model. I'll let you read through this. So here's now, we take the conceptual model, we need to translate to internal model, right? Remember, we take abstraction. The first layer is conceptual modeling, which we did through ERD diagramming, entity relationship modeling diagram. And then, and then we translate each of that to actual code that is needed to tell the database to actually make it happen. So this is the code to create this table or database table inside the database management system. So we interpret the diagram, and then we started to generate or write the implementation, internal model of the code. So this is what it's trying to describe. Right now, you don't have to understand what the code is actually doing. We'll get to that after the midterm. But you can see right now, this is a lot more complex to understand than looking at the diagram. But programmer lives in this world, so they need to understand and start writing this against your conceptual design. So that's what internal model is. So you can read through some of this. And then at the end, you have the physical model, which is the software, the hardware, the servers, the disk drives, the physical details about how to actually run the code. So when I run all this code, do I have the computer power, the space, the architecture to facilitate me running that? That's the physical layer. That's the actual implementation layer, which is the final layer of the abstraction, all the way to physical. All right. All right. So that is kind of the how we think through this throughout is abstract is progression. And then here's a table that kind of sums it up, so you can kind of read through external, conceptual, internal, and physical, and then you read some of the the attributes that describes it. And that is it. That is chapter 2. So the next will be probably your group project video that I will walk you through what you need to do in terms of designing a ERD diagram. All right, thank you.